And away we go. Okay. So the title of my presentation is IP Video and Audio Taxonomy, a Field Guide. And this is something that I've been, it's kind of a passion project, something I've been working on for a while now, but it's definitely a work in progress. It's not something maybe that will ever get finished, but really the idea here is I want to try to put a framework together to help people understand the different ways that you can analyze and compare and contrast all the different video and audio formats that are out there, so that you have a way to start conceptualizing about which things are important to you and which ones aren't, and how the different products fit together within that. So, why a field guide? Well, I mean, there's constantly, as more and more media production systems move over to IP-based systems, we're getting a lot of new formats. Things are proliferating. It's not like we develop a new standard and everybody stops and adopts that. That's not the way it works. And the reason for that is there's lots of different applications, and there's multiple sets of requirements. There's not any one consistent, format to rule them all. There's different products for different applications, different protocols, etc. So the idea behind the field guide is to help people understand, benefits and drawbacks. Which products, which protocols have advantages, which ones have drawbacks in certain areas, and what's important is what's important to you. In other words, some applications may be very, very concerned about end-to-end delay. Other ones may not have any interest in that parameter at all. So this guide is not meant to try to say which one's best or worst. It's just trying to sort them into some conceptual categories and allow people to try to understand what they are and try to understand how they might fit into their specific applications. So the inspiration for this was a book we had when I was a kid called, A Field Guide to the Birds by Roger Torrey Peterson. I kind of bastardized my own version of that, a field guide to IP video. But, the idea is that we're trying to help people identify and classify a lot of different species of protocols and tools and, types of ways of transporting video and audio over IP networks. So just trying to make it easy and friendly and nice for folks to use. So one of the things that I think is important is the thinking about how different protocols fit into different portions of the overall video supply chain. So if you start here on the left side, we're talking about remote venues and stadium applications, possibly remote studios. We're going to be using long haul networks in many cases to move video from those venues back to production centers. We're going to create programs. We're going to distribute those programs. One of the newest additions to this chart is the remote worker capability. So how do you support somebody who's working on a live production but isn't located in your facility or located at the venue? How do you use a proper video format that's going to work over somebody that might have a 20 megabit DSL connection to their house? How do you support them? You can't send full bandwidth signals, but you can certainly send some pretty useful signals that they can use to do their job on a regular basis. So at each point, at each step through this ecosystem, you're going to have different types of functionality that are required. You're going to have different types of tools that are going to be useful, and you're going to want to choose your protocol wisely. So down here, when we're talking about distributing things to millions of households, well, something that works there may or may not be of any benefit in the production scheme. And where they might be a benefit, for example, is that remote worker scenario. Maybe what you're doing is you're feeding somebody a live status of a particular piece of equipment or a video feed, using an HLS or a dash type of interface, because you know, first of all, that that signal is going to get through the firewalls and the other network headaches. It's going to allow you to have a secure connection because you can encrypt it and have both ends of the network secured by HTTPS or what have you. But you might sacrifice some of the real-time performance, and you probably are going to, have a heavily compressed signal in order for it to work in that environment. So you have to deal with the fact that they might not be able to see a perfect rendition of the image. Now, of course, if you condition their facility wherever they're living or working with a high-speed connection, make sure that that's up and running, and you have a way of making sure that it's available when you need it. Certainly, you can use other protocols that are going to give you higher quality video and probably require more bandwidth, and also probably offer you less delay. So it's a trade-off. It's always choosing the best type of signal that you need for whatever criteria you're going to be using for judging that particular type of protocol and for compression. So I love this quote. Actually, it's been attributed to a lot of different people. I used to think that a guy I worked for came up with this, but the nice thing about standards is that you have so many to choose from. That's very, very true in the IP video world. We have many, many different standards, specifications, things that are proprietary that a lot of people use, so they've become popular, etc. So more than any other place I can think of, there are just literally dozens of different standards that could play a role in any given video production environment. Any kind of workflow you come up with, you may use 5 or 8 different types of video transport, types of video compression, etc., depending on where you are within that workflow and depending on how you architect your particular system. So it's clearly going to be something that is going to continue to evolve. We've got some work going on in the VSF on new ways to make sure that video works well within a very cloudy environment. So the ground to cloud, cloud to ground environment, et cetera. We need to continue to innovate as new capabilities become available and as new requirements are placed on the market. So I don't see this situation, I don't see us reducing the number of video formats at all going forward. It's actually going to continue to get more complex. This is something that I've been working on for a long time. It's got a lot of animation, but the idea here is that we're trying to figure out where we came from. Where are the roots of all the video formats that are out there today? So one of the fundamental first texts, if you will, about how to put video over an IP network was Pro-MPEG Code of Practice 3. That evolved into SMPTE ST 2022-1 FEC and 2022-2, the format for putting MPEG transport stream packets into RTP. That in turn evolved into the VSF TR01 for delivering JPEG 2000 over MPEG transport streams, again using the 2022 format. If you want variable bitrate signals, those are also supported within the SMPTE standard suite. And if you want uncompressed, we also grew that onto this structure so you could transport every bit of an SDI signal over a network transparently and have forward error correction that worked at the packet level. From the uncompressed side, one of the foundation documents is RFC 4175. That was where my first exposure to the concept of P groups was, and that's the format that is being used extensively in ST 2110. AS67 was a foundational document for audio over IP that unified a whole bunch of standards and specifications that were out there for transporting uncompressed linear audio over IP networks. Those were combined into a first attempt of TRO3, which didn't really take off in the market. There were some technical nuances there that needed to be smoothed out. TRO4 was a way to sort of integrate TRO3 into the uncompressed 2022-5 and 6, the full SDI transport system. And one of the early formats that came out was the Aspen format in RDD 37. I had a chat with a friend of mine who should know what the future is there, and he basically said that in terms of this format, there's still a lot of it out there, but most, if not all, of the new installations that are going on today have moved away from that. If you're doing a brand new installation for a uncompressed IP video transport system, you're probably not going to be using RDD 37. So what happens here is that we have, of course, the birth of ST 2110. So what that's going to do for us is that's going to bring us a situation where we've got multiple different types of media. We're going to send these as separate streams, which was kind of a, and separate SDP files, which was an innovation beyond what we did in TRO3. And then we've got the system level doc, the video doc, the doc that describes how to send the packets out on the network. We have the audio format, and we have the ancillary data format, which is, of course, based on an RFC 8331 that Thomas Edwards helped champion through, that really documents how to convert the ancillary metadata into a IP packet stream. 2022-7 is kind of an interesting spec in that it's not tied to a specific protocol other than RTP. It can be used on compressed and uncompressed systems. 2022-8 was an evolution of TRO4 to realign the timing of uncompressed total SDI transport to 2110. And then we had AES 67, I'm sorry, not AES, AES3 signals being transported transparently over an IP network. We have a recommended practice 2110-23. That's involved with making sure that we have, gosh, I forgot 23 is, sorry. 2110-22 is compressed video of certain formats, typically high quality. Then there's a lot of activity going on in the compressed world. Again, we have RIST underway, which is a highly reliable transport mechanism using ARQ. We have TRO7, which is a way to do JPEG XS over IP networks. We have TRO8, which is a way to do JPEG XS over 2110 based networks. And we have IPMX, which is a brand new format that a lot of folks here in the Ames group are working on for lower cost 2110 systems. And recommended practice -24, which is focused on standard definition. So a lot of evolution over those years. We've got a lot of these things that we want to take a look at. So to sort of make sense of all of this, I came up with a few classification criteria, and they're listed here. We have compression, we have end-to-end video latency, we have error detection and correction, the code base, where can you get the code for doing this, the intellectual property, the network characteristics, etc. One of the things we could add to this would be, for example, encryption capabilities. So compression. So in each one of these categories, we have different types. In this case, for compression, we have uncompressed video, we have visually lossless compression, we have mezzanine level, and we have end user delivery. So for each one of those, we're going to describe what they are. So full video samples are transmitted in the uncompressed. Visually lossless, that was a little bit nebulous. It's kind of in the eye of the beholder. But the idea is that the output signal is indistinguishable from the source signal as judged by the human eye. We have mezzanine level compression. which is, very useful in contribution and maybe has some very good delay parameters, but maybe some video artifacts that you can deal with. And then, of course, the end user delivery types of compression that we're going to be using to push all those out. So for each one of these categories, I put in some examples. And maybe you don't necessarily agree with every classification that I'm going to make. But the idea here is to sort of start spreading these out a little bit, trying to see what the differences are. And it wouldn't make sense to have a category without anything that was in it. So the idea here was to start trying to quantify those and put those out. And yes, I admit I didn't go through all the different forms of MPEG compression. There's H.264 and 265, or HEVC if Matthew's on the line. We have, of course, good old MPEG-2 still being used a lot. Next one might be latency, so near zero latency, where it's very, very small amounts of end-to-end latency caused by the protocol itself. Subframe, you can have multi-frame latency, so that's going to be, not anything that's going to be using MPEG is going to have multi-frame latency because you have to do image comparison to make those things work. But you might have, something, like, one or more frames. So you might have JPEG 2000. It's going to be working on full frames. And then, of course, multiple seconds of latency. HLS and Dash are good examples of that. They would very much like to get some of the HLS stuff down in the fractional second end-to-end range. It's still a tough hill to climb. Even working on some new protocols to try to get around that, like WebRTC and things like that. Error detection and correction, minimal or no error detection, and that's in a lot of things that we standardize because we assume that that functionality is going to be done on a different layer. So, for example, IPMX doesn't have built-in error detection and correction, but there's no reason you couldn't send an IPMX system or signal over a system that supported a error correction or FEC type of environment. We have hitless protection switching, again, the good old 2022-7. That's all. That functionality is also built into the RIST specifications that have been out. Even the simple profile will support that. We have forward error correction, again, several different tools for doing that. And there are protocols out there that use various forms of FEC. We have ARQ functionality, so you retransmit packets that don't make it through. Two of the big proponents of that are RIST and SRT, along with a slew of proprietary formats. And then you have ones that work over TCP, which is probably one of the biggest challenges for real-time video transport. You have your code base. Where is the source code available? Do you have, if it's not available, how do you get it? Is it a license? If it is available, do you still have to pay a license? For example, you can definitely access the code that you need for H.264 and HEVC inside the FFmpeg libraries. But if you were to produce a product using those codecs, you need to pay the necessary licensing fees for that. And then there's other things that are, source codes available and there is no charge for the license. For example, RIST right now, the LibRIST is completely free and open, and anybody can use that source code to generate any product that they want. Intellectual property, another big thing that a lot of people worry about. Are they proprietary? Are they secret even? Are they proprietary, and is there a specification available for them? Is the spec open? Like RIST and NMOS and TR07 and TR08, even though they're not released yet, the intent is that those specifications will be freely available to anybody. Again, you might have to pay a license fee for example, for TR07. And then, some things are due process standards that have gone through a ISO recognized standards organization, such as SMPTE or AES or MPEG, folks like that. Then one other thing that always is important to think about is the network characteristics. Are the connections point to point? Are they multicast or point to multipoint? I mean, obviously you can't do true multicast on the public network, but you can certainly have one sender work with multiple receivers. Can you implement the protocol over a unidirectional network? And there's a few that do support that. Or are they required? Do you have to have a bidirectional protocol in order to support that? This is something that I found when I was doing a little bit of the research for this. I just thought I'd share it with the group. It's from a guy, I believe, at the Fraunhofer Institute that's been sort of tracking which codecs and which encryption schemes, and whether you can use stuff like CMAF and Common Encryption Codec for all the different streaming formats. So I thought I'd put that out there for people to look at. There's a link down here where I got it from, but I thought it was pretty cool and a worthwhile reference for anybody who's working in that area. So, as time goes on, we can add, new formats to these charts. For example, let's say we wanted to add SDVOE, which is a format that's fairly popular, or at least a lot of people are pushing it in the enterprise space, the Infocom world. We could go through, and each one of those charts, we could figure out how SDVOE would fit into them and figure out how we're going to make things happen. And we could also add new categories. We might want to add one on 8K support. We might want to add one on encryption support and things like that. So this is kind of a work in process. This is something that I think is important for us as an industry to keep in mind, that we've got these people that are thinking about using these technologies. They need to make wise decisions about that, and they need to understand how their decisions are going to impact their ability to achieve certain objectives for what they're doing. So that's what I had for today, and